So the pH and POH scales, we're going to talk about what these are. Yeah, I did this lecture this morning, and I think this just seems a little backwards. So let's just say what pH is first. pH is the negative log of the hydrogen ion concentration, or hydronium ion concentration. They're essentially the same thing. So this is a logarithmic scale, and what it does is it takes a very small number, like what did we say was the hydrogen ion concentration in a neutral solution? Remember? One times 10 to the minus 7th molar. Oops, I left out the 7. So when we take the logarithm of this number, we get minus 7. The negative here changes it to positive, and so the pH is 7. So a neutral solution has a pH of 7 where the hydroxide ion and the hydronium ion concentrations are equal, and we talked about that. On the pH scale, as you go to a lower number, it becomes more acidic, there's more acid present, and as you go to higher numbers, it's more basic. What's really nice about this scale is it goes from 0 to 14. It's a nice compact scale that's with easy to read numbers. No scientific notation, 10 to the negative 13 molar concentrations and things like that. And so it's just very useful that way. So you should know that pH under 7 is considered acidic. This divides it into weakly acidic and strongly acidic. You can say that. I just want you to know that below 7 is acidic, above 7 is basic. So it's a logarithmic scale, and let's look at how that works. Here, if we have a hydronium ion concentration of 10 to the minus 4 molar, we'll represent that as a dot. So each of these circles is representing 10 to the minus 4 moles per liter hydrogen ion. Well, the pH of that would be 4, because what we would do is we would take, let's see if I can write it in there, the negative log of that equals 4. This 4 is very much related to that 4. Okay? A base 10 logarithm asks, what power of 10 is this number? So 10 to the minus 4, what power of 10 is it? Minus 4. And we put a negative sign here to change the sign so that we don't have to deal with negative numbers. Okay? We made this up. Scientists made this up just like we've made up lots of things. And so if you're going to make something up, make it convenient, right? So that's why it's always positive. 10 to the minus 3, the log of 10 to the minus 3 is minus 3. You change the sign, you get 3. Going from 10 to the minus 4 to 10 to the minus 3 in concentration is a tenfold increase in the amount of hydrogen ion per mole. And then when you go from here to here, it's another tenfold increase. So going from this one to this one, it's 100 times larger in concentration. And since the range of hydrogen ion concentrations can range from like 10 to the minus 14 up to 1 molar or more, it covers 10 orders of magnitude, which is a huge, huge range. And so a logarithmic scale is really useful for that. So when we look at pHs, it's a little bit like looking at the Richter scale, which measures the intensity of earthquakes, right? An earthquake that's a 7 is 10 times as strong as one that's a 6, because it's a logarithmic scale as well. Any questions about that? So every difference in 1 on the pH scale is a difference in a factor of 10. So let me try to explain logarithms a little bit more. We did a little bit already. Let's make a column here. We'll have numbers in there, and then we'll take the log of x and see what we get. So get your calculator out if you don't already have it out, because you need to make sure that you can communicate with your calculator. I'll get mine out too. At least I think I can get it out. There we go. So find the log button. It says LOG on it. Your calculator should have one. So let's take a number like, I don't know, 100. So put 100 in your calculator and press the log button. Some calculators you have to press the log button first, and then the number, and then equals. What does it tell us the log of 100 is? 2. Well, does that make sense? Is 100 10 to the second power? Yeah, it is. If we express this that way, 100 is 10 to the 2. How about a million? 6. Because a million is 10 to the 6. So the log of it is 6. If we have a small number, like 0.001, the log of that's going to be -3. Because this is the same as 10 raised to the -3rd. Everybody with me? So when we're dealing with multiples of 100, logarithms are pretty easy to understand. Things get a little crazy when we start doing numbers that are not just multiples of 10. So let's make some more columns over here. So the log of 10 is what? 1, because 10 is 10 to the first power. So here we've got 10, and here we've got 100. Without using your calculator, what could we say about the log of 50? 50 is between 10 and 100, right? So the log of it should be between 1 and 2. And we might think it's halfway, because 50 is close to halfway between 10 and 100, but it isn't on the log scale. So put 50 in your calculator and find the log. And 1.699, just going to round it off a little bit. So it's a lot closer to 2 than it is to 10. And that's because this is not a linear scale, it's a logarithmic scale. Let's do something like 3.6 times 10 to the -5. Now you need to be careful with your scientific notation, because otherwise your calculator can think that you're putting in 2 different numbers, and it may take the log of only one of them. So on my TI-30XA, I do 3.6 EE minus 5 and press the log of it, and it's going to show me 4.44, but a negative number. Is your calculator cooperating with you today? No? Would you like me to speak to it? I got Andrew to get dressed this morning so I can make your calculator behave. Let's do another one. Let's do 3.6 times 10 to the -9. That's going to be minus 8.44. See if I'm right. Let's try 3.6 times 10 to the -14. That's minus 13.44. Is that right? So do I somehow know how to do logarithms in my head? No, that's a trick. So looking at these numbers, minus 4.44, minus 8.44, minus 13.44, what's the same about them? The numbers after the decimal point, right? And looking at these numbers, what is the same about them? The coefficient, the 3.6. The 3.6 always comes up as the 0.44. These numbers, the minus 4 is very much related to the minus 5. This is minus 8, that's minus 9. There's one different. Minus 13, minus 14. Because this number, 3.6 times 10 to the minus 5, is between 3.6, is between 10 to the minus 5 and 10 to the minus 4, right? It's more than 10 to the minus 5, but less than 10 to the minus 4. And so its log is between minus 4 and minus 5. So the reason I'm showing you this is I want to point out to you that when you take the logarithm of a number, any of the digits to the left of the decimal point come from this exponent. Is the exponent considered a significant digit? If we look at this number, 3.6 times 10 to the minus 14, how many significant figures does it have? 2. The 3 and the 6, right? The minus 14 is just telling us where to put the decimal point. So I'm not going to test you on this, but I want to tell you about it. When we're doing logarithms, the significant figures show up, I'm pointing in the wrong place, show up after the decimal point. So this number had 2 significant figures. When I take the log of it, I don't count anything before the decimal point, I only count what's after. So I'm going to use that rule, but I'm not going to test you on it. Okay, so those are logarithms. Here is the equation for pH, and you're going to want to write that on your note card for the final exam. By the way, I'm going to give you, it's your choice. You can either use a half sheet of paper and write on both sides, or a full sheet of paper but only write on one side. And by sheet of paper, I mean 8.5 by 11. Okay, not 10 by 17 or 16 by 20 photographic paper or something like that. Okay, no microfiching the whole book. Not that that would really help you, but someone might be tempted. Okay, so this is the equation that you'll need to calculate the pH. So I think this next slide has some examples. Calculate the pH of each solution and indicate whether the solution is acidic or basic. I've been forgetting the last part of this question, so help me remember when we get to that point. So here we're giving a hydronium ion concentration, 9.5 times 10 to the minus 9 moles per liter. So pH, negative log. I get tired of writing H3O plus. Remember, the hydrogen ion is just a proton, and it is never out by itself. We understand that it is riding on a water molecule. It actually is the hydronium ion. But we don't have to write this all the time. Just like if I say, well, the 3-month-old baby was at Disneyland, and he went here and here, does that mean that he was crawling around on the sidewalk by himself? I mean, 3-month-old babies can't do that anyway, right? No, somebody was taking him. We assume that someone is with him. And so when we say H+, we're assuming that there's a water molecule. And you'll see these used interchangeably, so don't let it freak you out, okay? We don't want anybody freaking out today. It's Thursday. I don't know, what is a good day for freaking out? Monday? Sunday night is never fun. Anticipating Monday, right? So we're just going to put the concentration in here. So the pH is the negative log of the given concentration. So communicate with your calculator. And I come up with 8.02. Well, if when you do the log, it will come up negative, and then this minus sign says change the sign. Yeah. Okay, so I accidentally erased the answer to the first one, but it was 8.02. So let's do the second one. The pH is going to be the negative log of that concentration. When you take the log, it'll give you a negative number. Change the sign. So the pH for this one is 2.21.
Would it always be negative log?
Yes. Yep. pH is always negative log. Negative log is not anti-log. It's the log of it with the sign changed. And the pH is almost always positive. And all the problems that I give you on an exam, they'll be positive.
So A is basic and the second one is acidic?
Yes. Yes. The first A is basic and the second A. The second A. Okay, now it's a B. And B, yeah. See, I would have forgotten it again. Thank you. So then the question, acidic or basic? So we're looking at this, we're comparing it to 7. This is higher than 7, so this one's basic. This one is less than 7, and so that solution is acidic. And today in lab, you're going to measure the pH of some different solutions. Any questions about calculating pH? Okay, so what if, instead of the hydrogen ion concentration, they give you the pH and they say, okay, what's the hydrogen ion concentration? Or what's the hydronium ion concentration? Well, this is the equation. I can show you how I got that. Does anybody want to see it? I didn't think so. Okay, nobody this morning wanted to see it either. If you have a desire to see it, but you don't want to raise your hand, I'll show it to you privately. It's just rearranging with logs, but it's, it's something that I would not expect you to know how to do. So write that one down. Okay, that one belongs on your note card. You'll need this equation in lab today. So here's an example for that. Calculate the hydronium ion concentration for a solution with a pH of 8.37. Well, we can't use the pH equals negative log of hydrogen concentration because rearranging it is unpleasant for most students. So we're going to use the equation that I just gave you. And that was the hydrogen ion concentration, or the hydronium ion concentration, is 10 raised to the power of the negative pH. And this looks weird. I know it looks weird. So 10 raised to the negative 8.37. Basically, we're undoing the thing we were doing in the last problem. That's a period, not a comma. 8.37. So now you have to learn how to tell your calculator to do this. On my calculator, TI-30XA, 8.37, change the sign to make it a negative number, then press the 10 to the X button. And what it shows me is a little deceptive. 1, 2, 3, 4, 5, 6, 7, 8, 9. But if I tell it to put that into scientific notation, it shows me this. So, do we have any issues with calculators? Okay, I'll come around. Okay, so this is an example of a kind of fluky thing that can happen on your calculator. my calculator has enough decimal places that it can show this to me in decimal notation. And so if I have it set up that way, it'll show it to me in decimal notation. But it can only show me the first digit. And so if you're doing this, and one of the choices on the multiple choice is 4.3 times 10 to the minus 9, and another is 4 times 10 to the minus 9. I don't think that would happen, but you might be kind of tricked into choosing the wrong answer. So most of your calculators will allow you to switch to scientific notation, and then it'll show you the rest of these digits. If it will not do that, one way you can trick it is when you get a display like this, go ahead and count the decimal places so that you know that it's 10 to the minus 9, then multiply it by 1,000 to force the decimal point over, and then it should show you the rest of those digits. So it's this 10 to the, something times 10 to the minus 9 will get you this weird situation where you only see one digit, even though the calculator knows what the rest of them are. So any questions about calculating? This is the right answer right here, the 4.3. Any questions? You'll get some practice doing these calculations in the lab today. Okay, pH is the negative log of the hydrogen ion concentration. POH is the negative log of the hydroxide ion concentration. This lowercase p means negative log of. And so there are situations where people are concerned about pCa, which would be the negative log of the calcium ion concentration. So the p just means negative log. So sometimes we're interested in the hydroxide ion concentration instead, and so we've got this guy right here. I showed the morning class how to derive the relationship. They weren't super interested, but if you want to see it, you can watch that video. I'm just going to give it to you. pH plus POH equals 14. And so there's another very useful equation. And going from the POH to the hydroxide ion concentration, the equation looks exactly the same as it does for the hydrogen ion and the pH. So those are a couple more useful equations. So calculate the hydroxide ion concentration for a solution with POH of 4.25. They're giving us POH. So what might happen is that you might look on your, you've got your note sheet for your final exam where there will be questions that could be like this. And you may have faithfully written down all these different equations that I've been giving you. And then the trick is to choose the right one. So here they're giving us the POH, and they're saying calculate the concentration. So you want to use this one, right? Because this is the hydroxide ion concentration equals some other junk with POH. So is 10, this time to the negative 4.25. Let's see. Turn on the calculator. .6 times 10 to the minus 5 molar. Now here's a question. Is that acidic or basic? Okay, so I've got both answers. The person who said basic very definitely at first is actually correct. The POH moves opposite of the pH. So if the pH is less than 7, it's acidic. If the pOH is less, it's basic. Because pH plus pOH equals 14. So if the pOH is 4.25, that's not a 2. It's not even close to a 2. Then what's the pH? Well, it's going to be 14 minus 4.25, right? Which would be what, 9.75? Did I do that right in my head? 9.75, we look at that. Oh, that's greater than 7. That's a basic solution. Okay? So don't feel bad if I tricked you, because I kind of expected that. Bless you. Okay, before we do that, I want to show you something. I call this the circle of pH. It's a little bit like the circle of life, except without the cute animals. And we can start this anywhere. pH, I did it this morning and it ended up looking different. It's just tipped on its side or backwards or something. So these are the 4 different values that we've talked about. We've learned how to convert between pH and hydrogen ion concentration. There were 2 equations, one for each direction. pH is negative log of the hydrogen ion concentration. And the hydrogen ion concentration was 10 to the minus pH. We also learned that we can go back and forth between pH and pOH. And that relationship is pH plus pOH equals 14. And that 14 is directly related to the ionization constant for water, 10 to the minus 14. We can also convert between these two. So pOH would be negative log of the hydroxide ion concentration. And the hydroxide ion concentration would be 10 to the minus, that's not a very good 0, 10 to the minus pOH. And then this one we learned about on Tuesday. Do you remember the relationship between those guys? They go opposite of each other because they're in an inverse relationship. They are related by the equilibrium constant expression for the self-ionization of water. Oh my God, that didn't help at all. It was this guy. The hydrogen ion times the hydroxide ion concentrations are always equal to this same number. So if this one's going up, this one has to come down, so that when you multiply them, they always equal the same. So what is all this good for? Pretty sure that on the homework questions for this chapter, they won't just ask you, oh, here's this, calculate that. Or here's this, calculate that. They'll do something unpleasant like saying, here's the pH, what's the hydroxide ion concentration? And you'll go, I don't have an equation for that. And you don't. You just do it in 2 steps. So let's just do an example of that. So give me a pH. A number between 0 and 14.
7.6.
7.6, thank you. 7.6. So they're going to say, oh, the pH is this. And they're going to want to know what the hydroxide ion concentration is. They say, calculate that. Well, you have 2 choices. You can go around the circle to the left, or you can go around the circle to the right. Which way looks easier? If we go to the left, we have to do this guy. Yeah, I think this guy's easier. Doesn't he look easier? That's just adding. I like this way better. Okay, But that's my preference. If you want to go the other way, it works just fine. But we'll go around to the right. So from knowing what the pH is, we can calculate the POH. Because the POH is going to equal 14 minus the pH. And that's going to be what, 6.4? That's the POH. From POH, we can find the hydroxide ion concentration using this equation right here. So the hydroxide ion concentration is going to equal 10 to the minus, not 7, 6.4. So we do need the calculator for that guy. So 3.98. Since this should really only have one significant figure, I'm going to round that off, but I'll write this out first. So I'm going to call that 4 times 10 to the minus 7 molar. I'm using one significant figure, you can't see it down there, because this pH, the 6 is the significant figure. The 7 has to do with where the decimal point is. So if you are given one of these 4 quantities, you can calculate the other 3, whichever one they ask you for. And that is the circle of pH. Any questions?